If you remember, at a point in the video, Okopa said the dot product of I and I is 1. Let me emphasize on this. The dot product of I and I, where the alphabets are the same, is 1. But the dot product whereby the alphabets are different, the alphabets which represent the directions of the vectors or the vectors themselves are different, we have 0. For instance, I.j is the same as I.k, which is the same as ij.k, which is 0. Why do we have the dot product of the different alphabet 0, but whenever the alphabet dot itself or the vector dot itself, we have 1? Do you think you can answer that? This is because the alphabets I and J are just representing unit vectors for our proof. Because they are unit vectors, the magnitude of I is equal to 1, and the magnitude of J is also equal to 1. Now we know from our scalar dot product formula that some vector I dot some other vector J is equal to the magnitude of I times the magnitude of J times the cosine of the angle between them. Let theta represent the angle between them in this specific situation. Now, if the angle between them is 0, which means theta equals 0, we are going to have this result, which implies cosine of 0. But cosine of 0 is 1. Therefore, the magnitude of I, which is 1, times that of J, which is 1, times the cosine of 0, which is 1, is going to give us a dot product of 1. But if the angle between I and J is 90, then we are going to have cosine of 90 over here. And we all know that the cosine of 90 is 0. Therefore, the dot product of any two different vectors from the I, J, and K space is 0. But when the vector dot itself, we are going to have 1 in a particular instance because we said I, J, and K are all equal to 1.